This is the DE1 SoC board that we are going to be using in the labs. It has got an FPGA chip, this big thing right here, almost in the center, and that's where our digital circuitry is going to be implemented on this FPGA chip here. To provide inputs to our digital circuit, we can use these switches and these push buttons, and to see what the outputs are from our digital circuit, we can use the 7-segment displays here, and you probably can't see them, but there's a row of 10 red LEDs here that we can connect to the FPGA, and they can light up or remain dark depending on the output of the respective pins on the FPGA. The simplest types of digital circuits are instantaneous ones, where the output just depends on the current input. So to understand that, let's think of an example where that does not hold. If, for example, I wanted to have a counter to count the number of times I've pressed this button, then I would have to have memory, because at any instance in time, I might not have pressed any button, but it has to remember how many times I've pressed this button in the past. So it might start off as 0, I press it once, 1, pressed again 2. At this stage right now, I'm not pressing any button, but the output is 2 because it remembers what's happened in the past. We need flip-flops to build circuits with memory, and we're going to understand those later in the course. For now, the output is just going to be an instantaneous function of the current inputs. So it could be that when I press this button, the light goes on, but when I release the button, the light goes off. It could be the inverse. It could be the light's normally on, when I press the button, the light goes off. In fact, in our very first exercise in the lab, we're going to do both at once. We're going to have a single push button connected to the FPGA. From the FPGA, we're going to have wires going to 2 LEDs. And one of the LEDs will be off and the other one will be on. And when we press the button, they flip. The one that was on is now off, and the one that was off is now on. That's a very simple example of a digital circuit. To implement such a circuit, we need to do two things. We need to design the actual circuit itself, and then we have to wire it up so that the push button is the input and these 2 LEDs are the output. When we design an electronic circuit, how do we normally do it if it was analog electronics? Well, often we draw a schematic diagram. We draw resistors, capacitors, transistors. We could use Protel or some fancy software to help us, and we basically sketch out our circuit and physically wire it up so we have a graphical description of what our circuit does. In the olden days, you could also do that with the software that we're using, but they no longer have that feature there. And you may be wondering why. Well, after a little bit of using the alternative approach, which is to describe the circuit by using a type of a programming language, you'll never actually want to go back to the schematic design. So schematic designs are good for absolute beginners because they feel that they can get started, but they have many disadvantages that you will come to appreciate once you've learned about hardware description languages. Hardware description languages describe hardware. They allow us to describe the connections between the different logic gates and flip-flops inside the FPGA. The hardware description language that we will be using is Verilog. The other very popular one is VHDL, and if you are going to become a serious FPGA developer, then you'll probably need to know both, but it doesn't matter which one you learn first. And I've chosen Verilog because I find VHDL very verbose. And the best way to learn is by doing. And if you have to spend hours typing out long things, then you're not going to learn as fast. So personally, I think Verilog is a good choice. It doesn't really matter. Once you've learned one, you can pick up the other. So step 1 is to design our circuit, and we describe our design using the Verilog language. Once we've designed our circuit and even possibly implemented on this FPGA, somehow we need to get this push button to go into our circuit, and we need to get these two LED here to be connected to the output of that circuit. And I refer to that as wiring things up. Now, the way that happens is that on this development board, someone's already physically connected these buttons and LEDs to the different pins of the FPGA. This FPGA has got hundreds of pins. You'll be surprised how many pins it has on its bottom. And all we can do, because this push button is already connected to a particular pin, all we can do is tell the software Quartus that once we've designed our circuit, that this input that we've described in our circuit, we want it connected to a particular pin on this FPGA. And by looking at the manual that comes with this board to find out which pin this button is connected to, that's in the user manual for this board, then we can tell Quartus, well that pin number that this switch is connected to, we want that to be the input to the circuit I just described. And similarly, we do the same with these LEDs. The pins from whichever pin on the FPGA is connected to this LED here, that's fixed by the designer of this board. But we can tell our hardware design here that we want a particular output connected to a particular pin on the FPGA. And in that way, it will be wired up to this LED here. The wiring up is done separately from Verilog. Verilog describes the circuit. Another part of the Quartus software is where you do the pin assignments, because they're different things. Going back briefly to the design of digital circuits, when we do it using Verilog, we have an important benefit. If we were designing an analog circuit using Altium, for example, then we would have to draw our circuit one component at a time. We'd actually have to describe explicitly what hardware we wanted where. We want this transistor here, this resistor there, we want this capacitor connected to this transistor over here, etc. With Verilog, we can do that. We can be very precise. But we can also just describe the behavior of the circuit. We can say, we want a digital circuit that does this, and we describe it using a programming language that looks a bit like the C programming language. And then Quartus has to figure out how to build a digital circuit that implements that behavior. And that can save an enormous amount of time. What's coming up next is that I'm going to get out my electronic whiteboard and I'm going to go through the first part of the first lab. And then in our next lecture, we're going to start learning about logic gates and about Boolean algebra, which is a mathematical way of describing basic digital circuits. That is, circuits without memory.
Let's go through workshop 1 together. Because these slides are very detailed, I am going to skip a lot of them and only pause and talk to the slides where I feel I can add some value for you. We are going to build this circuit and implement it on the DE1 SoC board. There's a power supply not shown here, providing power to this switch. The output of this switch will either be 0 volts if the switch is off, or 3.3 volts if the switch is on. Now, the supply rails used vary. In the olden days, 5 volts was popular. Before then, sometimes even higher voltages were used. We will learn later in this course that the lower the voltage, the more power you save. However, you have a problem with noise. So in the modern era, we will find that the external voltages may be 3.3 volts. And in fact, inside the FPGA, the voltages can be getting down to around 1.1 volts. But that's not too important. The main thing to note is that in digital systems, we have got one way of signaling a logic 0 by using 0 volts, and some way of signaling a logic 1 using some other voltage, whether it's 5 volts or 3.3 volts, doesn't matter as long as the circuit within that region is using the same voltage. Because I mentioned that inside the FPGA it might use a different voltage like 1.1 volts, then there's actually some circuitry on the FPGA that interfaces, that changes voltage levels for you. That's a more advanced thing. So anyway, we can have either a logic 0 or a logic 1 flowing in here, which simply means 0 volts or 3.3 volts. The electrons that go down this path here are going to go through this LED here, which means that if 3.3 volts comes in here, then it's going to light up this LED here. If, however, we've got 0 volts coming in, then this LED is going to be off because the potential difference across it will be 0 in that case. That's the simplest possible digital circuit, and it's not really processing the signal, it's just transmitting the signal, if you will, transferring it from one point to another point. This lower branch, though, is actually processing the signal. This is our first example of a logic gate, and in many ways it's the simplest possible logic gate, besides a buffer which does nothing. This logic gate is called an inverter, and the bubble at the front signifies that it's an inverter there. And in terms of logic symbols, if a logic 1 comes in, a logic 0 comes out, and if a logic 0 comes in, a logic 1 goes out. It inverts it. If this is low, this is high. If this is 0, this is 1. If this is off, this is on. Remember, in digital logic, we can think in terms of 0s and 1s, or off and on, or low and high. They're just different ways of describing the two voltage levels. Low is 0 volts, and high is, in this case, 3.3 volts. So in terms of voltages, because at the end of the day, this is just made using transistors, and we'll learn how later. It's actually very simple. You only need 2 FETs to build this. If the voltage coming in here is 0 volts, then the voltage coming out here will be 3.3 volts. Of course, there are supply rails not shown here. This guy has to have some power to be able to be an inverter. And conversely, if 3.3 volts comes in here, we're going to have 0 volts coming out here. Now, if you have a voltage exactly halfway, you might be asking, well, what happens? Well, in theory, we don't do that to logic gates. In practice, it happens, and in practice, these are analog guys. Later on, we'll do some LT spice simulations to see exactly what happens. But in case you're wondering, if I'm able to put exactly half of a voltage that's halfway between 0 and 3.3 volts in here, then if this is ideal, I'm going to get out exactly the same voltage here, halfway between 0 and 3.3 volts. That's an analog phenomena because this is at the heart of it an analog device, but we don't use it that way. We only really care about what happens when the input is either at 0 volts or at 3.3 volts. And what should happen is that it just inverts it like that. Anyway, when I move this switch, what's going to happen is that this LED, which is initially off, when I move this switch up, this LED is going to turn on. And this LED is going to do the opposite because I've inverted the signal. So if 0 volts comes in here, I've got 3.3 volts coming out here and this LED is on. Whereas if I have 3.3 volts coming in here, this inverts it to 0 volts and this LED is off. It's important to understand the concepts on this slide. Because we've been given a development board, everything is already soldered onto it so that these LEDs are already connected to specific pins on the FPGA, and this switch here is already connected to a specific pin on the FPGA. Our circuit that we design, our digital circuit, simply says whatever comes in this input here, it's going to go straight through to the output here, and whatever comes on the same input here, it's going to be inverted and goes to another output here. That's our digital circuit, and we need to somehow have our digital circuit connected up to the right pin of the FPGA so that this switch drives the input here, and this output drives this LED, and that output drives that LED. That has got nothing to do with describing this circuit. Describing the circuit is done using Verilog to describe this circuit here with inputs and outputs. Instead, we need to use the pin assignment tool of Quartus to tell it what pin to connect A to, what pin to connect X to, and what pin to connect Y to wire up this circuit here. One confusing and annoying aspect of Verilog is that Verilog was originally invented to test hardware. You would take a digital design, you would describe it using Verilog, you would write some test code for it and actually test it out, simulate it in software. So Verilog was invented to describe existing digital hardware. The way we now use it is that we actually want to go the other way round, and Verilog was not designed to do that, but we want to describe hardware in Verilog that doesn't yet exist, and then we want our Quartus software to somehow build that hardware from our description of it. That's quite hard to do. It takes Quartus a long time to do it. The compile times are quite long, and it can lead to much confusion and problems unless you get experienced with it through practice. When we use Verilog code to create hardware, it's called synthesis. The top-level entity, which we get to choose in this setting here the name of, is very important. Remember how we mentioned that we have to wire up the pins of our FPGA to the digital circuit that we designed? And the only way that we're able to do that is if Quartus knows where our circuit is, where are the inputs and the outputs of our circuit. And it's the top level module in Verilog, or top level entity in neutral language, which is where the main inputs and outputs of our circuit are. In other words, our pin assignment is going to allocate the inputs and outputs of our top level entity to physical pins of the FPGA. Think of a module as an actual chip. So in this case, we're building a chip. It's got one input called A and two outputs called X and Y. So we visualize it with an A at the input and an X and a Y at the output. And everything in between here, between the module and end module, describes the hardware that goes inside the chip that we're building. If we have a look at the description here, we see that the output X is equal to A, so therefore the input A goes straight through to the output X, and the output Y is equal to the inverse of the input A, or not A, which means that the output is going to go through an inverter. Sorry, the input A is going to go through an inverter and out to Y. In this way, our Verilog code here has described this piece of digital hardware up here with one input, two outputs, X is equal to A, Y is equal to not A. When we created our project, we made sure to name the top-level entity exercise 1, and we're using the same name here, and so Quartus now knows that this input here has to be connected to a physical pin of the FPGA. So if I've got my FPGA here, it's got actual pins on it, lots and lots and lots of pins. Because this is how it matches up with the name of the top level module, when we do pin assignments, we can tell it that input A is going to be connected to a specific pin on the FPGA, and similarly the output X is going to be connected to a specific pin on the FPGA, and the same for output Y. If we choose these pins carefully, then we can make sure that the switch is going to come, the switch on the development board, which is hardwired onto this particular pin, will get connected up to the input of our design, and the two LEDs on the board, which are hardwired into this pin and this pin, we can connect them up to the output of our design through the appropriate pin assignment process. This is made possible because this module is given the name exercise 1, agreeing with what we told Quartus was the top level entity. So the top level entity is what gets connected to the physical pins of the FPGA. When we press the compile button, many things happen. And if you are familiar with how we design normal electronic circuits, then what happens when we press the compile button is going to make a lot of sense. So imagine we're building our own circuit by hand. The Verilog code we wrote describes the circuit we want. Equivalently, we can think we have a schematic in front of us, a diagram of the circuit we want. What we need to do is we need to go and order those components from the shop. We need to physically arrange them onto a PCB, and we need to wire up the components, design the traces on that PCB. A similar process occurs with the FPGA, in that this design has to end up on the FPGA. Now, inside the FPGA, as we will learn later, there are a whole bunch of logic gates, or technically lookup tables, and we have a case of the software has to work out which ones to use, and how to flick all the switches inside there to wire up the logic gates in the correct way. And since the logic gates are actually lookup tables, it actually has to configure the lookup tables to implement the logic gates that we want. So compiling the design is doing all these things. It's working out how to build the design and how to lay out the design and how to wire up the design, all inside the FPGA. I cannot emphasize enough the importance after compiling a design to look at all the warning and error messages. Some of them are annoying and they don't really refer to anything significant, but almost always if you have a mistake in your design, there will be a warning message, and if you overlook it, it might take you hours of debugging time to find out the problem. So always check the warning and error messages carefully. You can press on these individual buttons to toggle them, the different levels on and off, the different severities here, which can make it easier to find them. So first of all, start with all the error messages and get rid of those, then check all the warning messages. As we said before, the inputs and outputs of the module whose name corresponds to the top level entity are going to be connected to physical pins of the FPGA. This connection is done using the pin assignment tool of Quartus. Provided we are only going to implement very simple logic functions, the easiest way to describe our circuit is to use assign statements, saying what the output is as a function of the various inputs. Here we had only one input, but if we had two inputs, we could say that little x was equal to A and B if B was another input, and we'll learn soon what a logical AND means. In this case, the only logic gate we have is an inverter or a logical NOT, and we used it in here to say that the output Y is not A. So if A is logic 0, Y is a logic 1, and if A is a logic 1, Y is a logic 0. Remember, in terms of voltage levels, that means if the input's at 0 volts, the output's at 3.3 volts, and if the input's at 3.3 volts, the output is at 0 volts. Once you have entered your design into Quartus, you might be very keen to put it on the board and see if it works. For a circuit as benign as ours, where we just have a switch connected to two LEDs, that's fine to do. But if this design was the controller for a jet fighter, we wouldn't want to just put the design into a jet fighter, send it up into the air and hope that it worked. It's very important to test it out first in software before we put it inside hardware where things can go wrong. There's a long history of simulating digital circuits. Remember, Verilog was actually designed to simulate digital circuits to test their behavior, to check it. It's also useful at the moment, if you're not able to make it into the lab, that you can actually check your design at home without having to get hold of a board to try it out physically. And the software we used for this simulation is called ModelSim. ModelSim is separate from Quartus, but Quartus is able to call ModelSim, and that's perhaps the most convenient way of using ModelSim initially, and that's what we will be doing here. So we can write our Verilog code to describe the digital circuit we want. We can write some additional Verilog code called a test bench that describes the tests we want to perform. Basically, a test bench tells ModelSim what inputs to give to the design. So in our case, we just have a single switch as input. That switch can either be on or off. So our test bench is going to toggle the switch. It's going to have the switch off for a period of time and on for a period of time. And then we want to observe what the outputs are of our design. A more advanced test bench can check that the outputs are correct, but in this course, basically we're just going to look ourselves at the outputs from ModelSim and check that they agree with what we expect them to be. Here we have our test bench code, and if I can, I'm going to shrink it down to give me room to create some drawings over here. First thing to note is that Verilog can be used for two different things. The first one is for describing digital hardware, and that's what we did before to describe the circuit we wanted on our FPGA. The second use of Verilog is to simulate that circuit, and to simulate a circuit we have to provide inputs and display the outputs. Very much like in the lab, once you've built an electronic circuit, you're going to connect up signal generators to the input of your circuit and oscilloscopes to the output of your circuit so that you can see how your circuit works. Well, the statements here do generate inputs to our design, and they also display the outputs of our design. So this is like in the lab where we connect up our design. This part in here is where we load in our previous design. I'll explain that in a second. And everything in every module in Verilog I like to think of as a chip, but because we have no inputs and outputs here, if you like, this is a virtual chip. It's a chip with no connections to the outside world, but it's our virtual lab space where inside it we can build our design. In this case, we're going to import another chip into there, and we're going to wire up a signal generator and an oscilloscope, so to speak, to that digital design that we've imported from another file. If we start at the top and go down, the first thing we have is a timescale statement. We'll learn more about that later in the course. It's important to include it here. For the moment, just have 1 nanosecond / 1 picosecond. We'll worry about that later. The next thing we have is our virtual chip. I'm calling it a virtual chip. It's something I've made up myself, the name, because it's got no input or output, so that's our lab space. I still like to think of it as a chip, so I'm going to draw it as this big chip here, but it's just got no pins. It's got no inputs and no outputs to the external world. Inside our chip, we can create more hardware, and in particular, here we're going to put a new chip. Exercise 1 is the type of chip. In the real world, I can buy an a chip that is a flip-flop, I can buy a chip that is a CPU, I can buy a chip that is an exclusive OR gate, etc. Exercise 1 is the type of chip that I can go and buy. I can buy one, I can buy 100 of them. We defined it earlier. It's also a module, but it actually had inputs and outputs. So I go down to the hardware store and I buy this chip exercise 1 and I put it inside my virtual chip. Here it is, right here. The type of chip this is exercise 1. If we look back, we see that exercise 1, that chip, has got an input that's called A and two outputs, one called X, one called Y. We need to connect this up with our own design inside our virtual chip test inverter. We could in principle create, go and buy more new chips and have extra chips here and wire up one chip to another chip, etc. But in this simple case, all we want is to have our signal generator connected to the input, and we just want to display what's coming out of the outputs here. In order to do this, we need to have some junctions to refer to by name. So to make life easy, we're just going to create 3 junctions here. I need one junction for the input, which I'm going to call gen input, Gen input, and I need 2 more junctions, one called out X and one called out Y. It's just like in a circuit diagram. If I'm drawing a circuit here and I'm allowed to pick any spot I want and call this point maybe Z, and then I can refer to Z as this junction here sitting between the 2 things. And I can say that this resistor, one side of it is connected to junction Z, and this transistor here, its emitter, is connected to junction Z as well. So these are just junctions. Sometimes we call junctions wires, sometimes we call them registers, REG. Verilog's a bit funny, that'll become clear later on, but for the moment, just think of these guys all as nodes or junctions that we can use to wire things up with. The wiring up of this chip, I've created this chip, I need to tell Verilog how to wire it up into my virtual chip here. And the safe way of doing it is the way it's done here. When we created module exercise 1, we gave it an input called A and outputs called X and Y. And A, X and Y must correspond exactly with the names we used when we created exercise 1. By the way, hello is just the name of this particular chip that we bought. I could have gone and bought 10 chips of exercise 1, and then I could have called them hello, goodbye, see you later, and 7 other names. Each chip gets a unique name so that you can refer to it if you ever need to. We just have one chip, although it's called hello, that doesn't matter for now. Its type is exercise 1, and in here, this part describes how we wire it up. And it should hopefully be obvious that the input called A is connected to the junction gen input, like that. The input of exercise 1 that's called X is connected to the junction out X. And the output Y of exercise 1 is connected to the junction out Y, like that. Inside our virtual chip test inverter, we have fully described the hardware. The only thing that remains is to generate input signals and have a look at the output signals. The way we generate signals is given in this part of the code here, and it's the only time you should think of Verilog like a C programming language. Initial means that this block between begin and end gets run as soon as the simulator starts. So Verilog simulators do many things in parallel at the same time. If you're not used to concurrent programming languages, that might be unusual. you'll get used to it by the end of this course. So initial means as soon as we run the simulator, start doing everything going from the begin to the end here. The very first thing it does at time t equals to 0, because that's when we started it, is it sets gen input, the junction gen input, that gets set to the value of 0. So the way we can show this is using a timing diagram. I can have time along the bottom here. At time 0, I have got 3 junctions that I'm interested in. I have got my gen input, I've got my out x, and I've got my out y. Because this is a digital design, each of these nodes here is either going to be a 0 or a 1. In physical terms, either 0 volts or 5 volts, for example, but it's either on or off, and so that we can display its current state using a diagram like this. What this means is that at time t equals to 0, it's initially a 0. At time t equals to 1, it jumps up to a 1. At time t equals to 2, it jumps back to a 0, and so forth. A timing diagram. That's not what happens in this circuit. Let's have a look at what exactly happens. At time t equals to 0, the gen input is set to 0. So if gen input is here, then initially it's at a 0 or a low state. Once I've set it, it doesn't change its value until the values change somewhere else in my code. The #10 tells us to wait 10 units of time. Well, what's a unit of time? That's what this first part of the timescale tells us. This 1 nanosecond says that 1 unit of time is 1 nanosecond. So #10 means wait 10 nanoseconds. So at time 10 nanoseconds, I'm going to execute this statement here. This is a display statement. It's going to display to the screen the current value of gen input, or the current value is 0 because that's the last thing we set to it. And it's also going to display the values at out x and out y. Now what are these values? Well, remember Verilog simulators do many things in parallel. Although we only have our code here that's generating the signal, we have actual hardware that's being simulated. As soon as we set gen input to 0, that value of 0 here goes into our exercise 1 chip, which remember looks like this. And that means that the output x here is going to take the value 0, the output y is going to take the value 1, and so out x is going to be 0, and out y, that node, is going to be a 1. So therefore, after having waited 10 nanoseconds to give everything time to settle down, this display statement is going to print out 0 for the input, out x is going to be 0, and out y is going to be 1. Then immediately after doing that, we change gen input to a 1. So on my diagram here, I haven't caught up yet, my gen input is 0 along here, all the way up until 10 nanoseconds, and out x is going to be 0, and out y is going to be 1. At 10 nanoseconds, my input is going to jump from 0 up to a 1. As soon as the input changes to a 1, the output here will change to a 1, and the output here will change to a 0. And so on our timing diagram, we get that this one jumps up and this one falls down here. After waiting 10 nanoseconds for things to settle down, we now have our inputs and outputs 1, 1, 0 being displayed. It's very important that given any type of digital circuit like this, you're able to change the inputs and figure out in your head what the output is going to be and also represent it using a timing diagram here. At the moment, we assume our logic gates are ideal. As soon as the input changes, the output changes immediately. Of course, that's not possible in real life. Nothing can travel faster than the speed of light, for example, but we'll worry about that later. It's good to be able to test an ideal circuit because testing an ideal circuit can be done quickly. And if the ideal circuit fails, well, the real circuit's not likely to work. So you want to be able to find the mistakes quickly. And being able to test an ideal version of your circuit quickly means that you can find some mistakes very quickly. While I drew a timing diagram by hand by going through the test bench myself on the earlier slide, we see here the output of ModelSim draws it for us. At time t equals to 0, our input is a 0 and it stays 0 up until 10 nanoseconds, at which time the input changes to a 1. And therefore the output x is going to be a 0 up until 10 nanoseconds when it changes to a 1, and output y is going to be a 1 up until 10 nanoseconds, and then it changes to a 0. The FPGA that we are using, the Cyclone 5, has got 896 pins, and here they all are set out for us in the pin planner view. We can choose what pins are connected to what part of our digital hardware inside the FPGA. In this case down here, you see that our top level entity, it has got an input A and outputs X and Y, and we are going to connect pin AB12. I don't know where that is. You can look carefully for an AB and going across 12. So the pin AB12 somewhere in here, that pin is going to be wired up to the input A of the hardware that we're describing. And similarly, the outputs of the hardware describing X and Y, they get wired to physical pins too. And remember, this Cyclone 5 FPGA is sitting on the development board. It has got wires soldered up to it, connected to push buttons and LEDs, etc. So by looking at the user manual for the development board, we can find out what pins are connected to what other accessories there are on the board. So if we want a push button connected to this pin here, then we just have to, if we want a push button connected to this pin here, we can't change that. The developer of the board hardwired that in. If we want the push button to connect to our digital circuit, we first of all work out what pin it's connected to, and then connect that pin to the input that we want it to be connected to of our hardware design. Once we've done everything else, now is the time we can actually implement our design onto the development board. Now there's extra electronics that does this for us. We don't have to worry about the details. Just somehow Quartus is able to send a file to the board that tells it how to configure the FPGA. So I want to emphasize, and I'll do this a million times throughout the course, the FPGA is not a CPU. We are not programming it. We are configuring it. Once it's configured, it's just like an ordinary digital circuit that you soldered together by hand. It's not executing any code whatsoever. So Quartus takes our Verilog code, which describes hardware, and it builds that hardware inside the FPGA, or it configures it. And we need to send the configuration file to the board, and the software does this for us. Quartus has got a programmer tool, and its job is to take the configuration file that Quartus has produced and actually send it to the FPGA so the FPGA is correctly configured. At this point, once the FPGA has been correctly configured, hopefully you'll find that one LED is on, one is off, and when you flick the switch, they swap roles. If there is anything you don't fully understand, please ask for help, or please have a look through these notes again. If you put a lot of effort into making sure you understand everything in exercise 1, the rest of this course is going to be a lot easier. So don't rush ahead, go back, make sure you understand all the concepts.